Okay, let's start. So next section is about a magnetic particle for biomedical. Okay, so now we consider the physical principle involved in application of magnetic particle in bioengineering applications. So shown here is the figures that we try to introduce the magnetic particle into your blood vessel, and this magnetic particle would be attracted by the magnet outside the tissue. So we may guide in the movement of this particle to any part of tissue. So the basic idea is perhaps for the bioengineers, they can coat something outside these magnetic nanoparticles, and the outside this shell there would be some ligands that would be sensitive to some receptor on the tissue. So when we first guiding this magnetic particle to the position of the tissue, then they will easily to connect together with some chemical reactions. So at that time you can remove the magnet, then it will automatically interact themselves. Maybe you can also use an external effect such as the AC magnetic field or AC electric field to induce the broken of these particles. Then you will release the different medical inside the tissues. So that will reach the goal doing some therapy. So this is the idea that we use the magnetic particle for the biomedical. So before that, let me give you a video. Okay, let's go to here. Okay.
This is Holly Grant. Unfortunately, Holly has a tumor, but recent advancements in nanotechnology now allow nanoparticles to help patients like Holly. Let's explore how nanoparticles are formed and their purpose. To create the nanoparticle, large molecules called polymers and drug molecules are placed together in a reaction pool. After controlling chemical properties such as the pH value, the polymers wrap around the drug molecules and form the nanoparticle. The nanoparticle then undergoes surface modification to keep it from being absorbed by other After being injected, the nanoparticles are affected by the large number of red blood.
Okay, I'm sorry about the voice that disappeared during the play. Okay, but actually, you just have the video give you some concept about how to use the nanoparticle inside the body and how to do the mechanism of the therapy. But in that video, we do not put the magnetic nanoparticle inside that. So the drug release is just need to is freely movement. So sometimes that will reduce the chance that this particle go to the correct side. But if you put a magnetic nanoparticle inside it, you can guide in that by the magnet, so that would be much easier, or you can reduce its dose for these medicals. That means they will also reduce the damage to the normal cell. Okay. So this case is how to target the drug delivery. So we introduce the drug called magnetic particle into the blood vessel and apply an external magnetic field. And typically for those blood vessel is paramagnetism, and it also responds from entities such as the hemoglobin. And it will also have some diamagnetic response. For example, most proteins, they contain a carbon, hydrogen, nitrogen, and oxygen atom. These kind of elements are all diamagnetism. Actually, I just mentioned in the previous class that is all kind of the atoms, they have the diamagnetic response, but that would be relatively smaller than the paramagnetic one. But even though they have diamagnetism and the paramagnetism, the magnetic field that created by themselves will relatively less than the outer external magnetic field. So don't worry about the those tissue or organ will resist the external magnetic field. Okay, so this is the part of the how does this magnetic particle works. So I think I don't need to repeat that again because we already see the video. So in brief, that the caster release the magnetic particle to a position that very close to for example tumor or some tissue or organ. Then you can guide in that with the magnet. So when it go to very near the tumor or some position that you want to treat, then you can remove the magnet because you already modify the surface of this magnetic nanoparticle. This ligand will very easy to attract by the receptor. Then they will enter to the cell and doing the things that you want to do. For example, release drug, or we will go to hyperthermia, and we will talk about later. Okay, sometimes you want to separate the entities from mixed solvents. So you can also use this method to separate the compositions in a mixed solvent. Okay, so this is the case that we use the magnetic particle coated with a biocompatible polymer. And the coating will also help you to reduce the aggregations and also prevent the magnetic particle exposed direct to body, because sometimes the magnetic particles are toxic to the cell. And when you make this kind of magnetic particle, you can separate that by using the external magnetic field. So that would be look like these figures. So there are many kinds of entities. Then you can put some magnetic beads inside this solvent. Then they will, of course, these beads are already modified. So you put into the solvent, then some entity will attract by this magnetic particle, and you can use the external magnetic field to attract that, and pour out the solvent, and we put the solvent again, clean solvent again, and wash several times, and remove the magnetic field. Then you can get a clear entities that you want. And this kind of entity you can use to eject to or introduce to the blood vessel, doing some magnetic therapy. Okay, so sometimes the principle of the gene delivery using the magnetic particles. So the cell can be transferred, positioned between the magnetic field gradient and the nucleic acid with attached the particles. And we use the field, this gradient field will cause the particle to move toward the target cell. So the cell and enter the cell accomplished with endocytosis. So this is the plot for this mechanism. So the gradient magnetic field guiding this magnetic particle close to the cell, and in short that the cell will eat this magnetic particle. So when it enters the cell, the nucleic acid will release itself, and that will be doing some gene engineering, modify your DNA and repair some damaged DNA here. And the other method that we use magnetic particle for magnetic medical is magnetic hyperthermia. So let me play a video for you.
What do you think of when you think of an engineer? Someone who builds cars and bridges? Well, did you know that engineers also create things to make people healthier?
Hi, my name is Yana. I'm a professor in mechanical engineering department at the Polytechnic Institute. I'm working on magnetic nanoparticle heating, which has application in cancer and hyperthermia.
Deanna studies different methods to help people with cancer. To do this, she works with nanoparticles. Nanoparticles are really, really small particles, about 1,000 times smaller than a single cell. The ones Deanna works with are also magnetic.
So magnetic nanoparticle is a tiny magnet. They're used to locally generate heat in cancer treatment.
Wow! So these small nanoparticles can generate heat? How do they do that? If we put a magnet near the nanoparticles, they will line up with the magnet. If we want the nanoparticles to move, we can move the magnet, and the nanoparticles will follow. If we want the nanoparticles to move quickly, we can use an alternating magnetic field. The nanoparticles follow the magnetic field and move to always align with it. If the alternating magnetic field moves quickly, so will the nanoparticles. When they move quickly, they start getting hotter and hotter. If they're in the body, this can increase the temperature of the tissue around the nanoparticle, which is called hyperthermia. This can be very helpful when treating cancer. Let's look at an example. This boy has a tumor, but doctors are going to help him by using magnetic nanoparticle therapy. First, the doctor injects the nanoparticles directly into the tumor. Since the nanoparticles are really small, they move randomly around the cells. Now, the doctor puts the tumor in an alternating magnetic field. This makes the nanoparticles move very quickly. And if they move quickly, they will start to get hot, really hot. The temperature can get so hot that the nanoparticles start to hurt the bad cells, and the tumor can shrink over time.
So depending on the duration of the treatment and the temperature rise, the cancer cells can either die or become sensitized to other cancer treatments such as chemotherapy or radiation.
When we send the nanoparticles into the body, we need to add a coating. It's like a hard shell coating that covers the particles. The coating helps the nanoparticle work correctly without hurting any other cells. If you put a bunch of nanoparticles in your body without a coating, they could all clump together. This would be bad because they could clog an area in your body and not get to the right place. So scientists add coatings. They have to pick the right kind of coating that help the nanoparticles go to a specific part of the body that they are trying to help. This makes sure they are working properly, without sticking together to other nanoparticles. Since there are all different types of cells in your body, the nanoparticles are coated differently, depending on the types of cells they are trying to enter. How cool is that? Scientists and engineers like Deanna have to be curious and creative to come up with ideas like these that really help people.
It's so much fun to learn new things every day and come up with new ideas. It never gets boring.
In this design challenge, design a magnetic nanoparticle with a coating that can interact all different types of surfaces. Are you ready to make your own coated magnetic nanoparticle? Check out the activity on the Curiosity machine.
Okay, that's the idea of the magnetic hyperthermia. So I can skip this slide. Okay, any question here? No? So next section is the Magneto Carotid materials. So as its name, the Magneto Carotid magneto is used the magnetic field to decrease or increase the temperature of on these materials. So you can imagine that, use that to heat up or become a refrigerant. So the Magneto Carotid effect is a magneto thermodynamic phenomenon in which temperature change of a suitable material is caused by exposing the material to a changing magnetic field. So shown here is the figure for this mechanism, and it's typical code in by the physicists called adiabatic demagnetization. The principle is something like this. So let me show you an equation here. So the internal energy is equal to temperature times its entropy. The entropy in the magnetic system is like this. If we have random oriented spins, then the entropy would be larger than the spins that align to single directions. So this entropy would be smaller. So adiabatic means that there is no any change to its internal energy U. This is called internal energy. So if this is a constant, you can imagine that if this is a constant, if we decrease the entropy, that means the temperature will rise due to the entropy decreased. In contrast, if you increase the entropy, then the temperature will decrease at the same time to keep the U is constant. Okay, so let's get back here. Go back here. So typically we have a kind of magneto carotid material. Then this sample carries spins, but in beginning their spins are random oriented. when we apply magnetic field in adiabatic process, that means we are there is an isolated chamber. We isolate it to the environment. So the only one way to change its temperature is by applying magnetic field. So for that principle, I just write in the whiteboard. When we apply magnetic field and align its spins, then its entropy decreased. Therefore, its temperature will raise, becomes T plus delta T. And then at this moment, we remove its adiabatic situation. That means we make contact with environment. For example, if there are some chamber, you can put this sample attached to the chamber. Then its temperature will go to will decrease and go to the normal temperature at the beginning, right? But the only difference between these two situations is, although they have same temperature, but the spin state is different. In this case, we have ordered spin state, and in this case, we have a random spin state. But in practically, their internal energy is reduced due to its entropy become smaller. So at this moment, when we remove its external magnetic field in adiabatic process, that means we just, for example, and I can make a sketch here. So in the beginning, there is a chamber, and the surface of chamber have a temperature T, and there is a Magneto-Carotid effect sample, and it carries random oriented speed, and we suspend it in this space and apply the external magnetic field. And then when it spins, becomes parallel. And here's the temperature T, and this is the T plus delta T. But the magnetic field is still exists. Okay. And now we just attach this sample to chamber. So the temperature goes to T. But at this time, magnetic field is still exists. And now we detach the sample to the chamber. And at this moment, the temperature is still T, and the magnetic field is exist. Okay, let's go further. So if we remove the external magnetic field, then spin will start becomes random oriented. So that the temperature is become T minus delta T. And so in this case, we got a lower temperature, and we can let this one to load another sample, because this sample Magneto-Carotid compound would become a kind of virtual refrigerator, because it had lower temperature. So if you put the sample here, you can cooling this sample. Okay, this is the idea how to use the adiabatic demagnetization. So this is the figure of its operation. That would be something like identical to the engine, but I don't want to mention too much about it. So here is some history of the magneto-carotid material. So in the late 1990s, these two guys report the magnetic entropy change in this sample is have a 50% larger than the report for the gadolinium material. In the early year, we know the gadolinium metal have a magneto-carotid effect, so we call it MCE. But at the 1990s, these two guys found this kind of sample have even larger MCE effect. So scientists try to improve its performance. So this kind of material have contains giant magneto-carotid effect we call GMCE, and not only have a GMCE, but they occur also at a very high temperature, which is 270 K, is close to 0 degree. Although it's a little bit relative to gadolinium, but I think it would be have some potential for industry use. So since the MCE occur below room temperature, this material would not be suitable for refrigerator operated at room temperature. So that means we need to looking for GMC compounds that operate at the room temperature at least 300 K. So there is another alloys has demonstrated the GMCE includes this one, and this one. Okay, you don't need to remember that. I just tell you the history. So this kind of material is good, but unfortunately they used a lot of rare earth elements. Okay, at that time, I mean the end of the 20th century, the rare earth element is still very expensive, and nowadays it's not so expensive, but it's still a cost. And so people try to looking for different kind of material that we don't need a rare earth element. So the nickel magnetite combined with X is gadolinium, cobalt, indium, aluminum, antibody. So this kind of material we call Hoyster alloy, and this kind of Hoyster alloy also promising candidate for magneto cooling application, because their Curie temperature is near the room temperature. So the GE, they announced they developed a functional NIMN based magnetic refrigerant. So that means we can cool it by applying magnetic field. But in practically, we still do not find any kind of magnetic refrigerant products because its efficiency and its temperature, working temperature, is still not so ideal compared to the traditional refrigerant. But it's just an idea that maybe you can use that in the specified environments. For example, if you go to the space, if you want to keep the temperature at a certain temperature, you need to this kind of magnetic refrigerant. Okay, hope one day we can see the magnetic refrigerator. We can cooling down instantly by this kind of GMCE material. Okay, there are another magnetic materials that are very important, which is the superconductors. Superconductor is also very important for the normal material, because people is still looking for a kind of conductor that without any energy loss when we deliver the electricity. But nowadays the discovery of the superconductor is still processing, but we still did not find the room temperature superconductor. Although there are several reports tell they found superconduct at the ambient temperature, but the operation environment is still very hard because for those room temperature superconductor, they need to working at extremely high pressure, so it is not able to reduce its working price. Okay, so the superconductivity is a phenomenon for exactly zero electric resistance, and there will explosion of magnetic flux field. So this explosion we call the Methadone Effect. They will repair all the magnetic flux inside the superconductor. So the good description of superconductor is not only zero electric resistance, it also need to contain the Methadone effect. Okay, so it's another characteristic is the superconductor have a critical temperature, and these two phenomena only appear as the temperature less than the critical temperature, we call TC. So a superconductor can be type 1 and type 2. For the type 1 superconductor, it has a single critical field, and above this critical field, its superconductivity is lost. And for the type 2 superconductor, it has two critical fields. So in between, it allows the partially penetration of the magnetic field. So let me make a sketch here. For typical superconductor, any kind of magnetic flux will repel by the superconductor. So you will find the magnetic flux will be go outside the superconductor. Okay, this is a superconductor. And for the type 2 superconductor, they allow the partially penetrate of this magnetic field, because it allows the magnetic flux pass through a certain point that's surrounded by superconducting current, and this superconducting current will pin the magnetic flux only at some point. So that would be control and limited the destroy of the external magnetic field. So at the other surface of this superconductor, they feel zero magnetic field and remain hold superconducting. So this is the principle why the type 2 superconductor can allow the partially penetration of the magnetic field and still hold superconductivity. Okay, shown here is the superconductor that's just floating above a magnet here, because this is the Methadone effect. The magnetic flux support this superconductor. We call it levitation or floating above to this magnet. We call it levitation. So in 2012, an advanced material article claimed the superconducting behavior of the graphite powder after treatment with the pure water at a temperature as high as 300 K and above. So far, they also have not been able to demonstrate the occurrence of the clear Methadone phase and the vanish of the material resistance. So they claim they found a room temperature superconductor, but they cannot repeat that experiment again. And in 2014, an article published in the Nature suggests that some material, notable YBCO could be made to superconduct at room temperature using the infrared laser pulses. But in this kind of operation, it is not easy for real electricity delivery because you need to use the pulse laser to induce its superconductivity. That's not practical for the making any kind of conducting wire, because you cannot use the pulse laser to expose all point of this conducting wire. And in 2015, an article also published in the Nature by the research of Max Planck Institute. They suggested at extremely high pressure, the H2S will transition to the superconducting from H3S around 1.5 million times atmosphere pressure. So that's very huge pressure, because and this kind of compound you need to put into the diamond amine cell. So that's also not practical to make a superconducting wire. And in that case, the critical temperature is 203 K, which would be the highest TC ever recorded at that time. And their research suggests that the hydrogen compound could be superconducted at up to the 260 K, which is match up the original research of Ashkoff. So this one could be repeated by another group and confirm that the hydrogen atom may be a kind of potential superconductor, but its room temperature is TC is still less than the room temperature. And we also need to create that kind of superconductor at a very extremely high atmosphere pressure. So in 2018, just 4 years ago, these guys from the solid state and structural chemistry unit of the Indian Institute of Science and Bangalore claimed the observation of the superconductivity at the ambient pressure at the room temperature. And what kind of the sample? They are in the fin and the pellets of the nanostructure material that composed of the silver particle embedded in the gold matrix. So that means that would be very expensive, right? A lot of research, but then they are found in the later paper in the 2019. And this claim is yet to be verified and confirmed. So it seems to me that there is still not another group confirmed this report. And also at the 2018, research noted that a possible superconductor phase at 260 K in the lengthening decahydride at the elevated pressure, which is really high, is 200 gigapascal. So it's also 1,000 times than the ambient pressure. So I say the scientists still pay their effort to looking for this kind compound if they can reach to their superconductor critical temperature can reach to a very high, close to the TC, close to the room temperature. So this is the holy grail for the scientists. If we can find a room temperature superconductor, that would be very great. And if they don't need to some special treatment, for example, high pressure, or they need to only operate in the very low magnetic field, and so on, then this kind of superconductor may be win the discovery of this superconductivity or superconductor may win the Nobel Prize, because that will give the huge contribution to the power delivery and that will reduce the energy disposed and help for green energy industry. Okay, there is something more a little bit weird, which is in 2019. So the U.S. Navy, they claim that a room temperature superconductor can be built using a wire with the isolated core and the aluminum PZT, lead zirconium titanium, and cold disposed by a vacuum evaporation with the thickness of the lantern penetration depth and the polarized after the deposition. So a scientist that work for the U.S. Navy has filed for a patent. Okay, they already applied the patents on the room temperature superconductor, represent a potential paradigm shift in the energy transmission and the computer systems. Okay, although they try to apply the patents, no one knows if this kind of devices did work with room temperature superconductor. But at least you can check if the U.S. Navy did have this kind of pattern. So here is the history of the discovery of the superconductor. So the first superconductor is beginning at the 1911s. This is because the Annis, who is the first one liquefy the liquid helium. The boil point of liquid helium is 4.2 K, and the Tc of the molecule is 4.3 K. So how lucky of the Annis, because there's only 1 point below than the Tc of the mercury. So he discovered in both the liquefied liquid helium and found the first superconductor of the mercury. And at that time, he also tried the lead. The ordinary temperature of lead is about 7.2. And he also tried to another different pure metal, which, for example, is niobium. And he also tried in different samples, for example, niobium nitride and niobium-3 tin. And nowadays, we still use the niobium-3 tin as a superconducting wire because it's alloy, which is easy to in longer to make a conducting wire, and it also contains a very large critical magnetic field, so it can carry a very high electric current. So at that time, people tried to looking for the alloy superconductor, but since 1985 or 6, the couplet, I mean the compound that contains CuO, is another branch for the superconductor, and this branch of superconductor is the most studied family. So the most familiar superconductor is YbCO, the yttrium barium copper oxide. So its critical temperature is about 90 K, which is about 77 K of the liquid nitrogen. So that means, because the liquid nitrogen is very cheap, you know there are almost 75 to 80% nitrogen in the air, so you can liquefy that very easier and get a cheap environment for those superconductor. So here they discover many types of the couplets. So the highest Tc of this couplet is the molecule-based couplet. But in practically, we don't want to use any kind of mercury products in your in the practical usage. because mercury is toxic for human body. Okay, so people try to looking for another different alloys, and they think about the alloy is easy to make and easy to become a wire. So there are different types. So at that time we also found the C60 is also a kind of potential superconductors, and they define its superconductivity with some dopes. For example, they dope the potassium. Okay, so since the beginning of the 21st century, the MgB2 is also another a very hot superconductor because it's not a couplet compound. It's pure. It's pure. We can so-called a kind of the alloy, but its critical temperature is still low, because that in this y-axis we found it the unit is in K, so the 40K is really low. It's not practical for usage. And there is another family we call the heavy fermion superconductor, and this kind of family is just for research interest, because the OTC is really low, even below the 4K. So this kind of heavy fermion superconductor are mostly included uranium. So you also know uranium is a radioactive element, so it is not able to. It is impossible to become lifetime use. And nowadays there is another different series called the FESE. This is another potential superconductor that is made by ion and selenide, and its ordinary temperature is close to 100 K, which is also about the liquid nitrogen temperature, boiling temperature. So that would be very good for practical usage. And here is the label. The liquid helium temperature is about 4K, so all of this kind superconductor you need cooling down by the liquid helium. And for the liquid hydrogen, its boil temperature is at the 20K, so all of this kind superconductor you need cooling down by liquid hydrogen. And the liquid nitrogen is here, and here is the CF4. So we try to push the ordinary temperature, but nowadays we still far away to the room temperature. Okay, so there is some basic idea about why the superconductor can have a superconductivity. So the first feature of the superconductor, they have zero resistance. How do they get the zero resistance? They are also correlated with the spin. So the superconductors have a kind of virtual particle we call a Cooper pair. Pair means we need to have two electrons. The one electron carries a positive spin, and the other carries a negative spin. And when these electrons move inside the compound, it also carries momentum. So in one particle, it carries up spin with the momentum plus h bar k, and the other is spin down with the minus h bar k momentum. So in this case, the total spin is 0, and the total momentum is also 0. So its moving velocity is also 0. But when we apply the external electric field, so we close here, then we will also have the situation that is this spin of this electron is also spin up and the other is also spin down, and its total momentum is h bar k plus delta k. The h bar delta k is coming from the moving force, driving force that's come from the electric field. So in this situation, the total spin is still 0, but the total momentum would be 2h bar delta k, and its moving speed is h bar delta k by m, actually 2me. So you can see that the electrons have its own mass center. So when the move of this electron around the periodical positive ion, then their mass center will hold straight no matter how this positive ion scatter one electron. So let me show you the animation. So they are starting moving. Okay, you can see that the mass center is go straight no matter how does this electron move. And one electron, if the one electron move up and other electron will move down, they will react immediately to keep the mass center go straight. So that's the principle why we have zero resistance, because the mass centers always go straight without any resistance or scattered by the positive ion. And the other effect of the superconductor is called the Methadone Effect. There are 4 figures. For the first figures, if we don't have any magnetic field inside the superconductor, in the normal state, which means they don't carry any superconductivity character, then when there is a zero field and we apply the magnetic field, then all the magnetic flux will penetrate to the superconductor. But when we go to the superconducting state, if there is zero magnetic field inside the superconductor, the applying external magnetic field will repel to outside the superconductor to keep the there is a zero magnetic field inside the superconductor. The third situation is in the normal state. When we apply the magnetic field here, then we are cooling down below the Tc, then the magnetic flux will be pushed outside to the superconductor. And if there is superconducting state, then there's keep always zero magnetic field inside its body. And when we remove its magnetic field, there are also still zero magnetic field here. If this one is the normal metal, when we remove the magnetic field, it will create internal magnetic field to keep the magnetic flux constant, because the lens effect tell you that they don't want to any change about its magnetic flux. So these 4 phenomena we call the Methadone effect. So in short, that is the superconductor always keep the zero magnetic field inside its body. Okay, so there is I know it's almost time to take a break, but I think if we can just finish this lecture, we may be close this class earlier. Okay, so just give me another 10 minutes. So for the superconductor, I just mentioned about that they maybe have a Cooper pair inside the superconductor. They will have anti-para spins, but they will connect to each other by a interaction force. So this spin up and spin down electrons connect to each other have a limited distance we call correlation length. If the electrons move far than this correlation length, then the Cooper pair will break and the superconducting current will become the normal current, and it will also feel the resistance again. So this correlation length we call it Kc. So if we make a superconductor nanoparticle, there's one problem, which is if the size, I mean the diameter less than the correlation length, or the correlation length or the diameter less than the magnetic field penetration depth. So let me recall that the magnetic field will destroy the superconductivity, especially for the type 1 superconductor. So the magnetic field is allowed to penetrate very thin layer of the superconductor. And when the magnetic field decreased to the exponential -1 of its stress, then this distance or this thickness we call the lambda. Okay, so when we make a superconductor nanoparticle, if this diameter or its size less than the correlation length or penetration depth, will the superconductivity disappear due to the size effect? So this is a dimensional problem, we may ask. And the other thing is, we know the two electrons will combine become a Cooper pair. So when they become the Cooper pair, then their energy will be lower than the normal state electrons. So this gap we call the Cooper gap. But when we reduce its size to the nanoparticle, we call a zero-dimensional system, then it will appear a gap called the Kubo gap. Okay, that's the pronunciation of these two words is very similar. Cooper gap and the Kubo gap. And the Kubo gap only allows the specified energy for the electron. So there is a problem when we reduce the size, become a nanoparticle. The Cooper gap will appear, and the Cooper gap is still exists. Will the Cooper gap influence to the Cooper gap? I mean, if the gap between the delta and the capital delta, they have some certain value where the electron allowed to form as a Cooper gap, or we can adjust the size to let this delta is equal to this one and allow the existence of the superconductivity. That's also another problem. We call it energy problem. So in these studies, we use the lead as the test species. So typically for this, there is the particle size. Okay, typically for the lead, its critical temperature is 7.2 K, and its critical magnetic field is about the 800 Oster or 800 Gauss. So for this size lead particle, its critical temperature will decrease with the applied magnetic field very quickly. But when we reduce the size, you can find there are 30 nanometer, 9 meter, 7.5 meter, 6 meter, and 4.5 nanometer. The rate of decreasing of its critical temperature would be gradually increased. So in this case, 6 nanometers lead nanoparticle will hold its Tc up to 6K when we apply the 9 Tesla magnetic field. So that's the totally different to the theory. Because when we reduce this size, the Cooper pair and its penetration depth will become the Cooper pair will destroyed, and its penetration depth is larger than the particle, which means all the magnetic will penetrate all whole particle and will destroy all kinds of Cooper pair. But in this case, we found the nanoparticle is not only resist the magnetic field, but also hold the Cooper pairs and form the superconductivity. So that would be very surprise for us. And when we further reduce the size to the 4.5 nanometer, we found the Tc decreased here. Because this is called Anderson effect. Okay, that's another effect that will reduce the Tc. You don't need to know that, but at least we know that when we reduce the particle size, the superconductor can resist even higher external magnetic field. So there is a sketch about the particle diameter against to the Tc and the diameter against to the critical field. So we found there is the critical field, critical temperature have a dramatically decreased due to the quantum size effect. When the particle size less than the 6 nanometer, the quantum size effect appear. So its Tc will decrease very faster. So we can calculate by theory to show you the critical size for those metals that layer Tc will become, which size that layer Tc will become 0. So this is the Cooper equation for the Cooper gap. You don't need to remember that. And if we know the Cooper gap of this kind of element, then that's the capital delta equal delta. We can calculate the diameter. The diameter can calculate from the valence of this equation. Then we can find out the limited size that the superconductor will lose its superconductivity. So this is the plot of the lead, tin, indium, aluminum, and the okay, this four metal. So for the aluminum, it will lose its superconductivity at the size less than the 6.9 nanometer, and for the indium that would be 5.1 nanometer, and the tin would be 5 nanometer, and the lead would be 3.2 nanometer. Okay, that's the latest discover for those metal superconductors. So what can superconductors do in the practical usage? So superconducting magnets are the some of the most powerful electric magnets we know. So we use that in the MRI or NMR machine, mass spectrometer, and beam scintillating magnet using in the particle accelerator. So they can also use for the magnetic separation, for example, for some medical usage that I just mentioned about in the previous section. Or they can use to extract the weak magnetic particle from the background that contains some non-magnetic particles. For example, they can use in the pigment industry. Okay. Any questions? No. Okay. That's all of this class. So next week we will hold the final turn exam at the 9:10 to 10:40. So that would be 1.5 hours. At the same time, on the Friday. So I think the teaching assistant already sent you a link to test. We will use the Microsoft phones to hold this final turn exam, but you need to check that link, because if you are not logged into with your school account, which is your school number at 0365 st.cycu.edu.tw. If you do not log in with that account, you are not allowed to enter the final exam link. So be sure that you can access the link that the teaching assistant give you, and when we go to Friday morning 9:10, the final turn exam link will provide that link to you. Actually, I can provide that to you now, because you are not allowed to access that before the 9:10 on Friday. So before that, you must take care. You need to test the test link first. Then please prepare your student ID. At that time, final turn exam, you need to present your student ID and open your camera all the time. The teaching assistant will roll call to check you are same as the picture on your student ID. Okay, so and please enter the final turn exam link in the 20 minutes of the beginning test. So that means you must enter this link, open this link, and open your camera in the Microsoft Teams like today before 9:30, and you can hand over your answer after 9:40, like a typical exam. Okay, but there is one thing you need to very careful. When you complete your answer, you need to click the submit button at the end of the test is not at the end of the Microsoft form. If not, you just click close, then you will not hand over your answer, and you will get a 0 score due to the wrong operation. So that would be very careful. You must click submit to finish your answer at the end of the page. Okay, that's really very careful. Another thing is, if you run out of your time, then the system will force to close your window. Therefore, you will not show your answer to me, and that would be got a 0 score. The system will tell me that you do not hand over your exam, so you will get a 0 score. So please answer and hand over your or click the submit button before the end of the time, which is the 10:40. Okay, but I think you will complete the answer before that, because there are only 20 choice quiz, so it's not so hard for you. But remember, read the lecture note in the iLearning, and I will also change the video link here. If you forgot anything that we just talked about, you can review that in the e-learning video link. Of course, you can also just read the lecture note. That would be also enough. Of course, there is another video record in the Microsoft Teams, depending on which kind you like. Okay, any questions? No? Okay, so we just stop here and see you next week. So please go online on time, okay? Not only in the Microsoft Teams, but I will give you the exam link and in the message board, okay? No, any questions? Okay, see you next week.
No, sir, I have a question.
Okay.
So when you say we need to check the link by ourselves, so recently I just tried to log in into my forms from your links, and I cannot log in into it.
Okay, so you want to access that the Microsoft link, right?
Yeah.
Then do you do you switch your account to your student number at 0365.csu.edu.tw?
Yeah, already. But the password say it's cannot enter. But I use the same password as these teams.
Yes, that's identical. But you cannot access that.
Yeah, I cannot access the account.
Can you share your screen and do that again for me?
Oh, sure.
Okay, please share your screen. And students, if you don't have any question, you can leave, or you can see how to operate that with Huang Fengsheng, right? Okay.
Can you see my screen, teacher?
Yes.
Okay, so this is my account, right? And this is password, but I cannot access it. It said the password is incorrect.
Okay, I think but this password, can you just type manually, not use the record your computer?
Sure.
Oops.
The same. It's incorrect password, but that's the only password that I use for my iLearning and this account. So I'm confused how to log in.
Okay. Can you try change the O following the H become the capital O? Can you change the O to capital O?
Capital O. Okay.
Yeah. Okay, type that wait. That's still the small. That's not a capital O.
It's a capital O already, but it's registered as a regular O.
Okay, can you click the sign option? Okay, sign to an organization. Okay. Click that. Oh, okay. I know that. So you just log in with your cell phone, right?
Yeah.
Can you log in with your computers, because the computer will register your organizations such as the CYCU, but you use your cell phone, it will register your personal account. So therefore, you cannot able to access the organization Microsoft phone.
Oh, I see.
So can you try
Okay.
that with your computer, not
Sure.
in your cell phone?
Let me try using my laptops.
So you found that this problem last time is just use your cell phone.
I haven't tried with my laptops yet.
Mm-hmm.
Okay, let me try.
So I know that Windows 10 and Windows 11, you are forced to log in with some organization or your personal account in when you in the beginning of the starting your open your computer. So if you are logging with your personal account, then you are not able to access the Microsoft phones. So that is a very bad strategy to us, because Microsoft plan to unify all the accounts to them, right? You are not allowed to use a personal account if you want to access some organization files. That's really bad. So sometimes we may confuse because we use the same account but are not allowed to log in.
I've already tried on laptops. It's also the same. I cannot access my account.
Okay. So let me think about. So your laptop is Windows system, right?
Yeah, my laptop is Windows.
But and can you access the Microsoft Teams with your laptop?
The Microsoft what? The Forms or the Teams?
Teams.
Teams. Okay, wait. Let me try it.
So other students have the same problem.
Wait, also, can I ask for the Microsoft Teams like this one? My student ID and O365C ST CYCU
Right.
The password is our iTouch, right?
Uh-huh.
Yeah, but I cannot enter as well. Oh my god. Can I somehow reset the password Is it possible?
Yeah. Sometimes because the school asks you to renew your password every half year, right?
Yeah.
So you just renew your password recently.
Okay. Okay. I think I get it.
Okay.
Wait.
Okay.
Okay.
So you can access the Microsoft phones.
Oh, I can access the question already.
Oh, okay. 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 So that's no problem, right?
Yeah. So this is have two questions, right?
Mm-hmm.
Awesome.
Yeah.
And should I submit this task on the final exams?
So you may remember this login password
Yeah,
so
sure.
to avoid any problem. Okay.
Yeah, sure.
Okay.
Thank you.
Okay, no problem. Okay. So we will see you next week. Thank you for your attendee. Okay. Then I will stop the record. And I will also disconnect the live broadcast to YouTube. Okay, let's